Hello everyone and welcome to Vibrations and Acoustics. Today we're going to find the equivalent spring constant for this particular system where you have a force pressing down in an off-centered way onto this platform, onto these two springs. Now if you're looking at this picture, you may automatically say that the springs are in parallel, and so you could use the quick parallel spring equation, but since this force is not directly in the center, that doesn't work because since it's pressing down, this spring will press down a little further than this spring, and you'll get a weird situation that you can't use the parallel spring equation on. So what we have to do is find the equivalent system, and looking at this, you can see that the equivalent system is going to be something along these lines. Combine the two springs into one spring at some location along this bar so that it's equal to the force, and you basically have the force pressing down right here. So that's what it's going to be like. So let's start out. We're going to use the energy method on this. So let's define the energies that we're going to be dealing with. So we'll call this one A, and we'll call this B for a moment. So the energies that are going to be used in this are going to be equal to 1/2 K1 times delta 1, which is the delta 1 is going to be the displacement here. And actually, I'm just going to draw another picture here before I go on with this anymore, so you get the deltas a little clearer in your mind. So this is like phase 1 when it's just sitting there, and then you have it kind of angle down like this as the force is applied. So you've got the force right there, and then you've got a force fighting it, F1 right here, and F2 right here, and just plain F up here. And then you've got a displacement delta, and then over here you've got a displacement of what we'll call delta 1, and over here a displacement of what we'll call delta 2. So this is the situation you're ending up with. This is a before and after. You've got the delta 1 and delta 2, but you're really focusing on where the force is because you have to get these springs aligned to where the force is, the equivalent spring aligned to where the force is in order to solve this problem. So the energy of this system, by just adding up the springs, is equal to 1/2 K1 delta 1 squared plus 1/2 K2 delta 2 squared. So that's the energy, that's potential energy that's being stored in the springs. Then if you look at UB, so that we can get a complete equation, UB, this is UA, UB is equal to 1/2 KEQ delta squared. So that's the potential energy being stored in this single equivalent spring right here. Okay, so now what we have to do is we have to figure out what these deltas are all the way around here. And to do that, you actually have to use the sum of the forces. So while we're using the energy equation to find the final values of K, we have to use some of the forces in order to find the displacement. So sum of the forces is equal to F1 plus F2 is equal to F. So that's equation 1. And then if we do moments here, I'll spell it out this time. Sum of the forces, sum of the moments, then you get F1 times L1, which is this force up here, F1 times L1, the distance to this point. You have to go around the point where the force is acting in order to relate the springs to this particular location so that you can align the spring to this force. Okay, so F1 L1 minus F2 L2, and that's because we're going to consider this to be negative. This is going to be a negative moment spinning this direction. So F1 times L2, or F2 times L2 is going to rotate that direction, which is going to give us a negative moment down here. And that's all equal to 0. Okay, so that means we have F1 L1 is equal to F2 L2. And no matter how you assumed the moment up here, positive or negative, this direction or that direction, you're going to end up with this equation eventually. So let's go ahead and solve for F2. F2 is equal to L1 over L2 F1. Okay, so there we have F2. Let's sub that back up into this equation and solve it again. So we've got F is equal to F1 plus L1 over L2 times F1. So here we have an F is equal to F1 of L over L2. And the reason it's L right here, L1 plus L2, which is basically what we're getting here if we were to get like a common denominator. If we were to multiply this by L2 right here, multiply it up, then and then factor out the F1, you'd have L2 plus L1 over L2. L1 plus L2 is just the total length. So we can skip a step and say, okay, L over L2 is equal to F1. So if you're confused about the algebra, just go ahead and start solving this and try to get it simplified as far as you can, and you'll see how that's happening. Just get the common denominator. Alrighty, so then F1 is equal to F of L2 over L. And again, using that relationship that we found earlier here, if we've got F1, then F2 is equal to F of L1 over L. Now, there's an interesting thing about this relationship, because if you're looking at it, you've got L2 over L, F1, L2 over the total length. So whichever side the force is on, F1, you take the length opposite to it over the total length, and that's the ratio you have. So basically, you're subtracting off this piece more or less within that ratio, and vice versa. So if you're a person who likes to memorize stuff, just remember that. The force of one is going to be the opposite side of the force being applied over the total length, the length of the opposite side of the force being applied over the total length times the force being applied. So anything on the other side over total length times the force being applied. Okay, so that's our two force equations. Now that we have those, we can go ahead and get delta, because since a spring follows the equation F is equal to kx, well, we have the force right here being applied, and we're looking for x, and we have the k for each one of these. So if we were to solve this, and let's say delta 1 is equal to k1, F1 over k1, well, now this is just going to be equal to F over k1 times L2 over L. And then similarly for 2 is equal to F2 over k2 is equal to F over k2 of L1 over L. Okay, so now the equivalent system has to, UA has to equal UB. The energy in this system has to equal the energy in this system. So UA is equal to UB. We go ahead and substitute those in now and start putting numbers, because we have delta 1 and delta 2. You sub it into these equations, which are set equal to each other. And you get 1/2 K1 of F over K1 times L2 over L squared plus 1/2 K2 of F over K2 times L1 over L squared. Remember, potential energy of a spring is equal to 1/2 KEQ of F. Here, let me double check something. Yeah, F over KEQ squared, which is equal to 1 over KEQ. Because you cancel that, and then all the F squareds cancel. Alrighty, 1/2, and then all the 1/2s cancel. Oh wait, KEQ doesn't cancel, I'm sorry. KEQ. Alrighty, so on and so forth. What else can you cancel? Anything else you can cancel here? Okay, so if you go ahead and finish that all up, what you should end up with, continuing on with that, is 1 over K1 times L2 over L squared plus 1 over K2 L1 over L and squared, which is equal to 1 over KEQ. And if you want to solve this out completely for KEQ, you totally can, but this is a very reasonable spot to start plugging numbers in. So that's how you find the equivalent spring constant for a system. You basically have to find the relationships in the deltas within the displacements with respect to the force being applied and the bar being moved. Find the equivalent energies for the full system and the equivalent system, and then move on down, calculate, and you get the final answer. So it's really not too bad. You just have to remember how to do the forces with respect to a specific location so that it's still accurate, and then also remember how to set up the energy equation. Alrighty.